Hi, this is Advanced Math, Unit 12 on vectors, Part D, page 4. So on the previous page, we looked at how you can find a vector that's perpendicular to a plane. And on this page, we're going to do the converse, which is if you have a vector, let's find a plane that's perpendicular. Now, the problem with just finding any arbitrary plane that's perpendicular to a vector is there, again, like the vectors, there was an infinite number of planes that are going to be perpendicular to any given vector. Think of it as a stack of planes, all of them parallel to each other. All of those would be perpendicular to a single vector. If one of those planes is perpendicular to a vector, then all of those stacked planes will be perpendicular to that vector. So the trick is that we want to find a particular plane that's perpendicular to a vector. We need to specify a point that we want that plane to go through. So to illustrate this, I'm going to do it first with a two-dimensional situation. Um, Following the instructions here, I'm going to do this one way. There are actually many, many different ways to do this example. I'm going to do it the same way it is in the answer key though. So first step, we're going to pick a point A on the grid and record its coordinates. Coordinates. So let's say I pick this point here. We're going to label that A. And again, you can pick any point you want. So that's coordinates 1, comma 3. Now, I want to draw a vector u on the grid. Well, I can start that vector anywhere and make it go in any direction you want. So let me try doing it, change my color again. I'm going to start a vector here, and I'm going to go to the right 3 and up 2. So, so that's my vector u, and its components are 3, comma 2. So I'm going to write that in. Here's my any vector u on the grid, and its components are 3, 2. And so we'll use those components. We're going to do this sort of the reverse of what we did before, where we took the coefficients of a linear equation and used those to form a vector. Here we're taking a vector's components and using them to form the coefficients of a linear equation. So these numbers are going to go down here and be transferred into the coefficients for the equation. So this becomes 3x plus 2y equals c. Now, the question is, where does the c come from? What do we use for the value of c? So what we're really defining here by saying 3x plus 2y is, so far, we're sort of getting at a family of lines that are all parallel to each other. And which of all of those lines that you choose is determined by the value of c. So what is the c in this equation? Well, we want, in this case, the one line that happens to go through point A. So what we're going to do is we're going to plug the x and y components of point A into the x and y in our equation, and we'll solve for c. So let's see if I can find a little room for that. The x and y components of A. So we're going to take this equation down here, say. So our equation is 3x. Now the x value that we're going to use is the x value of point A, the x coordinate of point A. And the x coordinate of point A was 1. And we're going to add to that 2 times y. And the y component, y we're going to choose is the y coordinate of point A, which was 3. And we're going to grab the c. We're just going to bring it down to c. So we have this equation now where we've plugged in for x and y the coordinates of point A. We have the coefficients 3, 2 from this vector u. And now we've got an equation. The equation says 3 plus 6 equals c. So c equals 9. So we've figured out that c is equal to 9, and that defines the one line that passes through point A, which is perpendicular to the vector u. So let me write this final equation down here. So I'm bringing these coefficients down from up here. 3x plus 2y equals, now the c value that I had from above, I just figured out what c is. C is equal to 9. So I have 3x plus 2y equals 9. So now I want to graph this. I've got an equation for a line, 3x plus 2y equals 9. Let's graph it. So I'm going to use the cover-up method, or the way you graph standard form linear equations. The x-intercept is when the y is equal to 0, so that's going to be at the point 3 comma 0. So I'm solving the equation 3x equals 9. The y-intercept, which happens when x is equal to 0, is going to be at 4.5. So it would be the point 0 comma 4.5. So I've got these two intercepts that I want to graph, 3 and 4.5. So let me go back up to my graph and plot those points. The x and y intercepts, go back to my other color. The x-intercept was at 3. The y-intercept was at 4.5. So that means we've got a line, and this line should pass through point A. It looks like it will. There's sketched in a line. And so the question is, does it look like, just by eyeballing it, does it look like this line is perpendicular to the vector u? And it certainly looks like it is. A nice perpendicular relationship between vector u and that line. So just to complete the bottom part of this page, the question is, so I graph the line, I graph the line above, does it go through A? Well, yes, it did. And was that line perpendicular to vector u? Well, yes, it certainly looks like it's perpendicular. And I haven't proven that, but I could certainly do that if I wanted to. So if you want to find the equation of a line perpendicular to some vector, use the components of the vector as the coefficients a and b in the linear equation, then plug in the coordinates of some point that's on the line to figure out what the value of c is. And here's the punchline. This also works for planes. So think about it. If you've got a vector in 3 dimensions and you want to identify the equation of a plane that's perpendicular to it and that passes through a particular point in 3 dimensions, you can use this exact same technique to do that. Now, think back to the original scenario here with the Yorkshire Canary bird cage at the Xenops Bird Ranch. We have a roof that's perpendicular to a pole that's used to support that roof. And the pole is at some crazy orientation, and the roof is at some crazy orientation. I think we have enough information now to figure out what the equation of the roof is. And so we'll get to that shortly, but on the next page, I think we have some more examples to work out.